So first, we go over the general principles of maximum likelihood estimation, the notion of a likelihood function, and then the important concept of asymptotics. I talked about this a little bit already earlier when we talked about the three classic tests, the wall test, the likelihood ratio test, and the Lagrange multiplier test, which were all based on this maximum likelihood principle. And I mentioned that the likelihood is actually kind of a measure of how probable is it that given specific parameter values and given a specific distribution that the particular sample is observed. So that's the idea. And then this notion of asymptotics, I already mentioned, that's how we get our properties. There's no small sample anything in spatial regression. It's all based on going to the limit. How do we go to the limit? And again, that's not classic textbook. It's actually quite complex. The maximum likelihood principle, as we've already discussed, is a general principle to guide estimation. You think of the data as a sample of a fully specified distribution. So, for example, a normal distribution, we will assume that the error terms in our spatial regression follow a normal distribution. And that is our entry point into maximizing the likelihood, which is the joint probability. And without a distribution, there's no maximum likelihood. Now, a more modern way of approaching this is called quasi-maximum likelihood or pseudo-maximum likelihood, which is acting as if there is a likelihood even when you know that it's wrong. And the main adjustments are with the standard errors. So you maximize a likelihood function that is built on an assumption of normality, even when there is no normality. And with the right kind of asymptotics, you get there anyway. So for practical purposes, it doesn't matter. Maximum likelihood estimation is then the methodology of maximizing this joint probability, which is a function of the parameters, and finding the parameter values that give you the highest joint probability, right? It's like I gave you the example of the count model, a Poisson model. What is the maximum likelihood estimate of the mean? You just keep changing it and finding out how many accidents could you expect, and then you see whether that matches what you observe in reality. Okay. So more formally, and this is an interesting contrast between classic statistics and Bayesian statistics. In Bayesian statistics, everything has a distribution, including model parameters, model coefficients. In classic statistics, the model parameters are constant. So they're unknown constants. You try to estimate them. In Bayesian statistics, they have a distribution. One that you assume beforehand, which is called the prior, and then one that you derive after seeing the sample, which is called the posterior. Okay. In classical statistics, the likelihood function is something that tries to find the optimal parameters given the sample. Okay. In Bayesian statistics, the sample, the probability of the sample, is a function of the value of the parameters. So even though they both use the concept of a likelihood, and they both basically use the same logic of likelihood estimation, the conceptual framework is flipped. Okay. In classical statistics, which is what I'm going to stick to for now, the likelihood is a function of the parameters, and you find the value of the parameters that give you the highest possible joint probability. For independent or even for uncorrelated normal observations, the joint probability is simply the product of the individual probabilities. If you take the log of a product is a sum, and that makes it very straightforward. Instead of actually doing this product, which is the joint probability, the actual likelihood, you use the logarithm of the likelihood, which is the log likelihood, because that then becomes a sum of logs of individual probabilities, one for each observation. So the joint log likelihood is built up by little pieces, one associated with each observation. As long as these observations are independent, you can just add them up. Of course, in our case, they're not going to be independent. They're spatially correlated, which messes everything up. And that's why we need special type of conceptual framework to work that out. Maximum likelihood estimation, as I already mentioned a couple of times, is essentially an optimization problem where you find the parameter values that maximize the log likelihood. And how do you do that? Classic calculus, first order conditions, second order conditions. So first order conditions is to find an optimum. Second order conditions is to make sure it's a maximum and not a minimum, right? First order conditions, first partial derivatives. This gives you a system of equations, typically taking this form, the partial derivative of the log likelihood with respect to each parameter. That has to be set to 0. You solve it. Unfortunately, in most situations, there is no analytical solution. So then you have to use numerical optimization to find the value of the parameters that gives you these 0 values for the partial derivatives. These things, we call them the score when we talked about Lagrange multiplier tests. So that's why in statistics, Lagrange multiplier tests are called Raoult score test, because this is the score. This is what we use to get that test. It's the same thing that we use as the first order condition. So it's all sounds very simple. You pick your distribution, that gives you a likelihood function. You take the log, that gives you a log likelihood function, which is a little piece attributed to each observation. You just add them up. You put it in an optimization framework. You find the first order conditions. You solve it. You're done. You have your estimates. What you don't have is any sense of the precision of those estimates. For that, you need the second order conditions. So we saw this figure before, as I used it to explain the 3 different types of tests, one on value, one on fit, and one on the slope. In maximum likelihood estimation, we try to find the parameter value where this slope is 0. Now we have to make sure that this is a maximum and not a minimum. And that's why we need the second order conditions. Usually, you know ahead of time because of the shape of the functional form, what it's going to be. But it's a very fundamental result of mathematical statistics. If you've never heard this before, it has to do with the information matrix. That's the mouthful. The negative expected value of the second order partial derivatives of the log likelihood. Because if it's second order, it's a matrix. So the first order is a vector, one for each parameter. Second order is partial with respect to first, and then partial with respect to second. First, third, first, fourth, second, first, and so on. So that's a full matrix. And that's why, I mean, ultimately, it ends up giving you the variance covariance matrix. So first, you get these partial derivatives, the second order partial derivatives. Then you get their expected values. So for that, you need the distribution to figure out these are all functions of the variables and the parameters, some very complicated, so it's not always straightforward to get these expected values, but you derive that. That's a matrix. Then you take the negative, and then you invert it. And that's the asymptotic variance matrix. So the asymptotic variance matrix is not the information matrix, but the inverse of the information matrix. Most cases, there will not be a clear analytical solution. So you can figure out the information matrix because that's just partial derivatives. Then you get the expected value, put in a negative sign. That, I'll show you for the spatial lag case, has a nice shape, something you can understand. But then the inverse of that, you don't know what it's going to look like. That's just a numerical thing, right? So 2 steps. First step is simple optimization. Find a solution using first order conditions. Second step, you need the second partial derivatives. You need this matrix, the information matrix, and then you flip it around. Good thing is this is the best you can do. It's highly parametric, which means you make a lot of assumptions. If these assumptions hold, you cannot do any better, in the sense that it's asymptotically on target. So if your sample is large enough, the estimate that you get from these first order conditions will be the population parameter value. So that's called consistency in large samples. In finite samples, we're concerned with bias. Here we're still concerned with bias. It gets a little complicated because a consistent estimator is not necessarily unbiased, but we're not going to go there. Let's just remember this is good, right? And it's as good as you can do in terms of precision. So of all the consistent estimators, it has the smallest asymptotic variance. Remember the parallel with linear regression and the Gauss-Markov theorem, where among all the unbiased estimators, OLS had the smallest variance, right? Here, among all the consistent estimators, maximum likelihood has the greatest precision, the smallest asymptotic variance. It's also normal in the limit. Of course, we assume normality to begin with, so there's no reason to lose that in the process. The good thing is in that modern, more recent findings have gotten the same properties without having to assume normality, but using more complicated central limit theorems and laws of large numbers. I'll talk about that in a second. The other thing is that, I don't know if we talked about this, but if you have an unbiased parameter, let's say you estimate a slope in a simple linear regression, and you're interested in the square of that slope. So if you have an estimate of the slope and you want to estimate the square of that parameter, the square of your unbiased estimate for the slope is not an unbiased estimator for the square of the slope. You have to actually figure out how the expected value of a function of a random variable, which your estimate is. It's a random variable. It has a mean. It has a standard deviation, a standard error. It has a distribution. So when you have a function of a random variable, it's not the mean of that function is not necessarily the function of the mean. If you've taken math stat, that's one of the favorite homeworks that you get. Okay, you get these functions, beta 1 and beta 2 and beta 3. What's the expected value of beta 1 squared plus beta 2 times beta 3, right? And go to bed, right? So with consistent estimators, you don't have to worry about this. In part, you don't have to worry about it because you're kidding yourself. you're acting as if you're working in this limit world, but you're not. Right? You don't really know how quickly you are close enough to the limit to assume that the limit properties hold. So this is invariance, which is exploited quite a bit in computations of things like elasticities in economics. You know, these are functions of the parameters. If you work with a consistent estimator, then the function of the consistent estimator is a consistent estimator of the function. You know? Whereas with unbiased estimators, that's the unbiasedness does not necessarily move to the function itself. And a very important caveat, but as I mentioned, not as important as it used to be, the properties only hold if the assumptions hold. And more recent findings, this gets mathematically very complex. But the good news is that this even works in non-ideal circumstances. So you probably all had some mathematical statistics at some point, and then you find these properties of consistency and asymptotic normality for independent observations, typically IID, independent and identically distributed observations, which means they have the same variance. None of that holds in the spatial case. And it's actually very complex. And I'm not making you read those papers. It's extremely complex because the initial derivations by Keith Ord, he kind of assumed that it worked. And he was right because it worked. But it wasn't, let's say, to the satisfaction of a theoretical econometrician or a mathematical statistician, because there was no unequivocal proof that it was consistent and it was asymptotically normal. So that didn't happen until about 30 years later with some new tools, which are called triangular arrays. And triangular arrays deal with the fact that, and I'll talk about that in a second, in space, you don't go to the limit by just simply adding new information, because you add information in a spatial context. Where are the neighbors? And specifically, the neighbor structure changes as you change your sample, which is not the case in the standard case. So if you imagine a square, right? A regular grid, let's say a 4x4 regular grid, and where we have a spatial autoregressive model, which requires a weights matrix. The weights matrix is based on that square grid, right? Now, if we add observations outside the grid, okay, so we're growing the sample, the neighbor structure of the border cells changes. In time series, that doesn't happen. In time series, if you add a new time period, the previous time period does not change. It's the same. In space, it does change. So this requires, if you're a stickler for theoretical results, a whole new mathematical framework that deals with that additional disturbance. In asymptotics, you don't want disturbance. You want smooth transitions, continuity, all that stuff. No sudden shocks, no changes in the weights, right? So how can we get the same results even with this additional complication? And that required new specialized laws of large numbers. Those are the ones that we need to get consistency, and new specialized central limit theorems. Those are the ones that we need to get the normality, okay? And that stuff is very complicated, and it requires different ways of thinking about it that allow some dependence, but not too much dependence, because if there is too much dependence, then, as I mentioned before, you don't win the rat race. It's a rat race about gaining information. And that's what asymptotics is all about. So asymptotics is about the rat race. As the sample grows, there should be, here it says there is, it really should be, there should be more information about the underlying parameters. And for that to be the case, there has to be smooth changes, continuity, nothing crazy. And that's why the other day I mentioned the importance of Tobler's law and the concept of distance decay applied by that. So everything depends on everything else, but closer things more so, which means things further apart less so. And in other words, if you move far enough away, you have, for all practical purposes, independent observations. And then you can use the usual asymptotics, but with some adjustments, because you don't get with each new observation an independent piece of information, but you get correlated pieces of information. So you need more of it before you get the same amount of information. But if you keep going far enough, you get to the same point, only it's not as quickly. So when you used to, in traditional textbooks, they would say 30 observations, you're good to go. In space, forget it, right? And depending on the method, it's not even a couple of hundred, it's 10, 20,000, 30,000 before it starts to kick in. So keep that in mind when you do your projects. I'm not making you do 10, 20,000 observations, but if you run this, say, for 49 or for 80, okay, the asymptotics are not going to be there. Okay, you act as if they are, but they're not going to be there. Okay, so this only works if we play by the rules. And I mentioned already, these rules are called regularity conditions. It basically means no crazy stuff, right? Not too much variability. You can have some variability, but not too much. So typically, mathematically, this gets translated into bounds on the second power or the fourth power or the sixth power of the variance or the error term. So either the variance or the squared variance and so on. So no infinite variance. Infinite variance means very extreme observations can happen. So you say, no, we can't have that, right? No nuclear explosions, no asteroids hitting the Earth. Okay, that can't happen. Moments must be regular over space. That's a very tricky one. It's called spatial stationarity. And in essence, it means you cannot have trends in space. You cannot have different parameters in different parts of space, which we call spatial heterogeneity. So how do you get rid of all that? You get rid of it by modeling it so that you end up at the end of the day with an error term that is stationary over space. So if it's spatially correlated, you take out the correlation. If it is heteroscedastic, you take out the non-constant variance. If there is a trend, you take out the trend. So that's how we deal with that. And people often get confused about this. You know, there's a model, y, x, beta, spatial axis, y, all that stuff. And clearly, this is not stationary. No, it's not. It is the means to get to something that is stationary, which is your error term. Everything is driven by the error term. As we'll see in a few minutes, the maximum likelihood estimation starts with the error term, not with the y, with the error term. So as long as our error term is well behaved, after we do all the adjustments, then we're in business. Okay? So at first sight, there may be kind of a disconnect between assuming spatial stationarity and, say, modeling spatial heterogeneity. That doesn't compute, right? It's contradictory. But that's not what it is. The modeling part gets rid of the non-stationarity so that you end up with something in the error term that is well behaved. And as I said, typically no crazy stuff. So restrictions on the degree of heterogeneity and the range of spatial dependence. So again, Tobler, no infinite range of spatial dependence. The longer the range is, the harder it's going to be to get to a sample size that is equivalent for all practical purposes to an independent sample size. You know, if you lose 10%, you need to have 10 times more. If you lose 50%, you need way more, right? And that is something that the way I look at it comes back to you after you've done your estimation. You look at the parameters, do these make sense, right? I talked a little bit about that, I think, when we did the lab for the SLX model, where we got some parameters for the neighbors that were larger than the parameter for the location itself. Well, that runs counter to this range of spatial dependence, okay? That you can't have that. If the dependence increases with distance, we're out of business. This doesn't work, right? So then we have these different formal frameworks. A law, I already mentioned this, but just to make sure, there's two different things. One is to establish consistency. So in essence, this means law of large numbers. You get more and more information as you get bigger and bigger samples, so that in the end, you have the mean, or your average is the actual population mean. And I mentioned an easy way to get some intuition for this is use random number generators. So use a generator, generate 10 standard normal random variables, take the average. It's not going to be zero. It's not going to be crazy either, but it's not going to be zero. You do this for 100, it's going to be a little closer to zero. You do this for 100,000, it's probably not going to be able to distinguish it from zero. So that's the law of large numbers. Our problem is all these samples are correlated, so we'll need more of them to get uncorrelated information. And then the second thing is a central limit theorem, which is not having normality in the limit, because we don't. As I mentioned before, in the limit, we have a constant. We have the true population parameter, which in classical statistics doesn't have a distribution. It's a constant. A constant cannot be normally distributed, right? So it's not in the limit. In the limit, we don't have a distribution. But as we go to the limit, we can rescale our variable, our estimate, so that the difference between the estimate and the true parameter follows a normal distribution. So first, consistency, a thing called uniform law of large numbers. I just give this to you in case you read papers and see this stuff and have no idea what this is. It sounds very complicated. It looks very complicated. It isn't very complicated. It's basically a principle, and of course you have to prove all this stuff, that guarantees that whatever you do with your sample gets you something that is close to what happens in the population. In other words, if you do the maximum of the likelihood of your sample, you're actually getting something that is close to the maximum of the likelihood in the population. So in the population, you have the true parameter value. You can figure out what would be the joint probability of your sample. You know what that is. That maximum, you know what it is. I mean, you don't, but as a concept, you know what it is. What you need is something that guarantees you that whatever you're doing with that sample actually is not nonsense, right? So what if I design an estimator that says, okay, my estimator is in a quantile, the 30 percentile point, okay? What I would have to show is that as the sample grows, that 30 percentile point actually gets close to my true population parameter, which it won't be, right? But in a maximum likelihood, and later we'll see the same thing when we do spatial two-stage least squares and generalized methods of moments, you prove that what you do in the sample, which is this, and what you have in the population, which is the second part, the difference between the two goes away. So for all practical purposes, you're fine. The other one is a little trickier. And a lot of people get stumped by this and get stumped by this square root of n part. But if you recall what I said, as the sample grows, in the limit, beta equals b. So there's no distribution. As you get closer to this, and if you rescale the difference between the two by the square root of n, why do you have to do this? Because as the sample grows, you have more n's, so you want to control for that. Right? In the limit, everything becomes super small because you're dividing by n. You're doing an average. So you want to rescale this, and then with the usual proofs, this gets very complicated in the spatial case, you get a normal distribution. So it's not that it's normal in the limit, but it is if you rescale the difference between your estimate and the true parameter by the square root of the sample size at that point, this rescaled difference has a normal distribution. In practice, you don't have to worry about this rescaling stuff because it's taken care of in the results for your estimation. If you remember, maybe you don't remember when we talked about two-stage least squares and the asymptotic variance, there were all these 1 over n's that then in the end all canceled out, okay? You need the 1 over n because if you don't do that, your magnitudes become infinitely large for an infinitely large sample, right? If you have a sum of your observations, if your sample is 10, you have a sum of 10. If your sample is 10,000, you have a sum of 10,000. Of course, 10,000 is going to be bigger than 10, right? But if you divide by 10 or you divide by 10,000, then they remain comparable. That's where this stuff comes from. Okay. In space, how does the sample grow? Now, in time series, you have the past, you have the future, you go to the infinite future, everybody knows what you're talking about. In space, it's two-dimensional. So it's not a one-dimensional increase. In 2 dimensions, how do you get a larger sample? And there's 2 ways to do this. Actually, there's a third, which is a combination of the 2, but I'm not going to go there. That's fun for mathematical statisticians, but it's not fun for us. So 2 main cases. One is called increasing domain, and it is what it says it is. Your domain becomes bigger and bigger and bigger. The other one is called infill. Your domain doesn't change, but it's like a sandbox. And you sample more and more and more in the sandbox. So ultimately, every grain of sand is counted, right? Those are the 2 approaches. The bad news is they're not equivalent. And so what we will cover in this course are methods that apply to increasing domain asymptotics. If you would take a course in geostatistics, that's Kriging and variograms and spatial interpolation, that's infill asymptotics. Interpolation, you fill in what you don't observe, right? Those 2 different things. Some estimation methods work in one, and most estimation methods work in one, but not in the other. So increasing domain, infinite space, unbounded, expands at the edges. So this example that I gave you with the grid, and you put an extra layer on the outside, then you put another layer outside of that, You just keep moving outwards. The number of neighbors doesn't change. In a grid, say in a rook system, the maximum number of neighbors is 4. You'll never have more than 4 neighbors, whether your grid is 5 by 5 or 10,000 by 10,000. It doesn't change. And that's very important. The density is constant. So there's a bound on the number of neighbors that you take into account. And increasing domain asymptotics is Kansas, right? This is, I'm not kidding you, this is Kansas. And so you have counties, you keep adding counties at the edge, and you grow the sample, right? You fill it up. Number of neighbors doesn't change. On average, a county has 5 neighbors. That's actually geometry. You can prove this, but on average, that's what you have.
Yeah. So it's not an assumption.
What is not an assumption?
The number of neighbors doesn't depend on that.
No. It's not. Yeah, it's a property. So because the way the sample grows, the neighbor structure is not affected if you have the right neighbor structure. So contiguity, fine. If you do crazy stuff with economic weights or socioeconomic weights, maybe not, right? You have to be careful. But with the pure spatial context, it works fine. Infill asymptotics is bounded space. Remember the sandbox. It's a container view, and you keep adding additional observations in the container. So let's say we want to model air quality in the US. We start with our EPA monitoring stations, hexagons. And then we get a lot of money. We put another set of monitoring stations. The US doesn't change. It doesn't move out. It's a box. It's a container. But we keep adding more and more monitoring stations, which means we get more and more observations. The density increases. The number of neighbors increases with the sample size. And sometimes that's a good thing because it gives you more information around every given point. But for other things, it's not a good thing, where you want a limit on the number of neighbors that are involved. And so this is infill asymptotics. These are actually house sales in Orange County, California. It's an example of a misleading map. This is an aside. Why is this a misleading map? Because of the size of the points. Okay. These are individual houses. There's no way that they are as big as they're shown on this map. So this is one example of how to lie with maps. Do a dot map with big dots, and it looks like, there's a very famous, well, maybe not that famous, but there's a map of foreclosures in Chicago. You might have seen it. It looks like all of Chicago is being foreclosed. It was like 7%. So because of the dots, the size of the dots, same shootings, carjackings. If you want to give an impression that crime is everywhere, make your dots big enough and it looks like crime is everywhere. If you make your dots teeny, there's no crime.